Good morning students, welcome back to physics class. In the previous class we were discussed about dual nature radiation matter. Today we shall continue the same chapter, that is dual nature radiation and matter. So in the previous chapter we had studied about photoelectric effect. On the basis of photoelectric effect we have derived the laws of photoelectric emission. We already studied about experimental study of photoelectric effect. So what conclusions on that see? So the first point is, for a given photosensitive material and frequency of incident radiation, the photoelectric current is directly proportional to the intensity of light. Okay? The saturation current is directly proportional to the intensity of incident radiation. So what is the first point? For a given photosensitive material and frequency of incident radiation, the photoelectric current is directly proportional to the intensity of light. So the first point is the photoelectric current is directly proportional to the intensity of light. Okay. Then the second one is, for a given photosensitive material, there exists a certain minimum cut-off frequency below which no photoelectrons are emitted. However, high is the intensity of incident radiation, and this frequency we call it as threshold frequency. Okay, so for a given photosensitive material, there exists a certain minimum cutoff frequency. That frequency we call it as threshold frequency. So below the threshold frequency, there is no photoelectrons are emitted. Okay. Then the third point is, above the threshold frequency, the stopping potential or equivalently the maximum kinetic energy of the photoelectrons is directly proportional to the frequency of incident radiation, but it is independent of its intensity. And the last one is, the photoelectric emission is an instantaneous process. Okay, so these 4 points you have already studied in the previous classes. So today we are going to continue the photoelectric effect, that means Einstein's theory of photoelectric effect. Okay.
In 1905, Albert Einstein proposed a radically new theory of electromagnetic radiation to explain the photoelectric effect. This theory addresses the contradictions between particle nature and wave nature of light. According to this theory, electromagnetic radiation energy is built up of discrete units called quanta of energy of radiation. This is also called the photon. Each photon has energy E equal to h nu, where h is Planck's constant and nu is the frequency of the incident radiation. When photons are incident on the metal surface, the electron of the metal absorbs energy from the photon. The minimum energy required for the electron to just escape from the metal surface is called the work function phi naught. If the energy absorbed by the electron is greater than the work function of the metal phi naught, the electron is ejected with maximum kinetic energy K max equal to E minus phi naught, where E is the energy of the incident photon. Let this be equation 1. This equation is referred to as Einstein's photoelectric equation. However, the electrons which are more tightly bound emerge with kinetic energy less than K max. Since kinetic energy cannot be negative, we have E greater than phi naught for photoelectric emission, and since E is equal to h nu, we have h nu greater than phi naught, or we have nu greater than nu naught. When nu naught is the threshold frequency of the metal equal to phi naught by h. Threshold frequency, nu naught, is the minimum frequency of the incident radiation required to just cause photoelectric emission from a metal surface. Since nu naught is equal to phi naught by h, we have phi naught equal to h nu naught. Let this be equation 2. Substituting the value of phi naught from equation 2 in equation 1, we have the maximum kinetic energy of ejected electrons, K max, equal to h nu minus h nu naught, since E equal to h nu. From equation 3, we observe that the maximum kinetic energy of the ejected electrons is proportional to the frequency of the incident radiation, nu, since h nu naught is constant for a metal surface. From this, we also observe that the maximum kinetic energy of the ejected electrons is independent of the intensity of the incident radiation. As the intensity of the incident radiation increases, the number of photons incident per second on the metal increases. Thereby, the number of electrons absorbing energy from the photons increases per second, and hence the number of electrons ejected per second from the metal surface also increases, thereby causing an increase in the photoelectric current. If V0 is the stopping potential for a certain frequency, nu, of the incident radiation, the maximum kinetic energy, K max, is equal to EV0. Let this be equation 4. Substituting equation 4 in equation 3, we have EV0 is equal to h nu minus h nu naught. Let this be equation 5. We observe from equation 5 that the stopping potential V0 is dependent on the frequency nu of the incident radiation, since h nu naught is constant for a given metal surface. However, the stopping potential V0 is independent of the intensity of the incident radiation and similar to the maximum kinetic energy. On rearranging the terms in equation 5 as shown, we get equation 6 as shown. Equation 6 is similar to the equation of a straight line y is equal to mx plus c, where the slope m of the graph is equal to h by e. From equation 6, as stopping potential V0 varies in a linear fashion with the incident frequency nu, a graph drawn between the stopping potential V0 taken on the y-axis and the frequency of the incident radiation taken on the x-axis is a straight line. Millikan performed the photoelectric effect experiment for a series of metals and found that the stopping potential V0 varied in a linear fashion with frequency and from the slope of the stopping potential. V0 versus frequency, new graph, determined the value of Planck's constant using the known value of charge on electron, which is equal to 1.6 into 10 power minus 19 Coulomb. The value of Planck's constant h is equal to slope of the graph into the value of charge on E. The value of h is found to be equal to 6.626 into 10 power minus 34 joules second. The intercept on the x-axis provides the value of the threshold frequency, nu0. The work function of the given metal surface phi0 is equal to h nu0 can be determined since we know the value of Planck's constant h. Irrespective of the intensity of the radiation, the photoelectric emission is an instantaneous process, as was experimentally verified. As you know, the phenomenon of photoelectric effect explains that light consists of packets of energy known as quanta, and this characteristic of light exhibits during its interaction with matter. Each such packet has energy E equal to h nu, where h is the Planck's constant and nu is the frequency of light that is being used. Einstein concluded that each packet of energy can also be associated with a definite momentum P equal to h nu by c, where h is the Planck's constant, nu is the frequency of the light used, and c is the velocity of light. Each quanta has definite energy as well as momentum, and hence each packet of energy can be treated as a particle, which is called photon. Now we can say that light possesses a particle nature as well. In 1924, A. H. Compton proved the particle nature of light with his experiment on scattering of X-rays from electrons. The phenomena of scattering of X-rays from electrons is called the Compton effect. Let's now summarize the properties of photons. In the interaction of radiation with matter, like in the case of photoelectric effect, it seems as though radiation is made up of particles called photons. Each photon has energy E equal to h nu. Since nu is equal to c by lambda, we have E equal to hc by lambda, where lambda is the wavelength of light used, and momentum P is equal to h nu divided by c. All photons travel with the same speed of 3 into 10 to the power of 8 meter per second through vacuum, irrespective of their frequencies. All photons of light of a particular frequency, nu, or wavelength lambda, have the same energy and momentum, irrespective of the intensity of radiation. An increase in intensity of radiation of a given wavelength implies an increase in the number of photons crossing per unit area per second, as long as the frequency of radiation is constant. Hence, all the photons of a given frequency still have the same energy and momentum, irrespective of the intensity. The rest mass of a photon is zero. Photons pass undeviatedly through an electric field, which can be created by the charged plates of a capacitor. Hence, we can say that photons are not affected by electric field, which means they are electrically neutral. The photons also travel undeviatedly in the region between the two magnets, and so they are not affected by magnetic fields as well. In a photon-particle collision, such as photon-electron collision, the total energy and total momentum of the system are conserved. However, the number of photons may not be conserved in such a collision. This is because the incident photons may be absorbed or new photons may be created. In the case of photoelectric effect, we have seen that the photon is completely absorbed in the process of photon-electron collision. When X-rays are scattered from electrons after the photon-electron collision, a new photon is created. The experiment conducted to study the photoelectric effect led us to conclude that radiation behaves as if it were a bunch of particles, while experiments conducted to study the phenomena of interference showed the wave nature of radiation. This particle wave nature of radiation was extended to matter by Louis-Victor de Broglie. De Broglie hypothesized that moving particles of matter display wave-like properties under suitable conditions. He reasoned that nature was symmetrical and that the two basic physical entities, matter and energy, must have symmetrical character. Hence, if radiation showed particle nature, so should matter. De Broglie proposed that wavelength lambda associated with the particle is equal to h divided by p, where h is the Planck's constant and p is the momentum of the particle. But p is equal to m multiplied by v, where m is the mass of the particle and v is the velocity of the particle. This equation is called the de Broglie equation, and lambda is called the de Broglie wavelength. The dual nature of matter is evident in the de Broglie equation. The left-hand side of the equation has the attributes of a waveform, while on the right-hand side are the typical attributes of a particle.
The next topic is de Broglie wavelength of an electron accelerated through a potential difference V. Okay, so here we have to consider an electron of mass m and charge E. Let V be the velocity acquired by it when it is accelerated from rest through a potential difference of V volt. Okay, so first you have to consider an electron of mass m and its charge E and its velocity is V. Okay, then you have to write the expression for kinetic energy gained by the electron. So which is equal to half into mv square. Here m is mass of an electron, then v is velocity. Okay, then and also you know that the kinetic energy is equal to what? E into v. Okay, so kinetic energy gained by electron is equal to what? This equation, that is work done on electron, is also same as that of kinetic energy, that is which is equal to EV. So you have to substitute these two equations, that is half mv square is equal to E into v. So from this equation you have to find out v. Okay, so v square is equal to what? V square is equal to EV, 2EV divided by m. So v is what? Root of 2EV divided by m. Okay, then how can you find out de Broglie wavelength? You know the lambda is equal to h divided by mv. Okay, here m into v is what? is momentum. Okay, lambda is equal to, you know that lambda is equal to de Broglie wavelength. Lambda is equal to what? H divided by P. P is equal to what? M into V. Then you have to substitute the values of V in this equation. So H divided by M into root of 2 EV by M. Okay, which is equal to what? H divided by root of 2 MEV. Okay, here E into V is what? Kinetic energy. E into V is kinetic energy. So this equation can also be rewritten as H divided by root of 2 M into K. Okay, then you have to substitute the constants values here. That is, H is a constant here. Okay, so H is what? H is equal to 6.63 into 10 raised to minus 34 joule second. Then M is mass of an electron was 9.1 into 10 raised to minus 31 kilogram. Then E is equal to what? 1.6 into 10 raised to minus 9 coulomb. So after that we got the relation lambda is equal to what? 12.3 divided by root V Armstrong. Okay, so which is the required relation. So lambda is equal to 12.3 divided by root V Armstrong. The next one we have to discuss about some numerical problems related with the dual nature and matter. So the first question is, what is the frequency of a photon whose energy is 66.3 electron volt? Okay, so what is the question? What is the frequency of a photon? So frequency means you have to find out mu. How to find out nu. Okay, is this frequency? So you know that E is equal to what? H into nu. Okay, so nu is what? Nu is equal to E divided by H. H is a constant term. We call it as Planck's constant. So in the question E is given, that is, what's the value? E is equal to 66.3 electron volt. Okay, divided by what? H. So what's the value of H? Planck's constant is a constant. Its value is 6.63 into 10 raised to minus 34. Okay, so here the energy is given in 66.3 electron volt. So you have to convert it into joule. So how can we convert it into joule? You have to multiply this with the 1.6 into 10 raised to minus 19. Okay, so then you have to solve this numerical values, so which is equal to 1.6 into 10 raised to 16 hertz. Okay, then the second question is, calculate the number of photons in 6.62 joule of radiation, energy of frequency 10 raised to 12 hertz, given H is equal to 6.62 into 10 raised to minus 34 joule second. So what's the question? Calculate the number of photons. That means you have to find out number of photons n. Okay, so in this question, which are the given terms? The energy of that photon is equal to what? 6.62 joule. Okay, then its frequency is also given. Its frequency is what? Nu is equal to 10 raised to 12 hertz. Okay, and also Planck constant is given. Is a constant term which is equal to what? 6.62 into 10 raised to minus 34 joule second. Okay, so you know that energy H nu is equal to what? E, which is equal to 6.62 into 10 raised to minus 34 into nu. Nu is what? 10 raised to 12. Okay, so which is equal to what? 6.62 into 10 raised to minus 22 joule. Okay, so already energy is given. It is, what is the energy? 6.62 into joule. By using this formula, H nu is equal to what? E, which is equal to 6.62 into 10 raised to minus 34 into its frequency 10 raised to 12, which is equal to 6.62 into 10 raised to minus 22 joule. Okay, the number of photons present in 6.62 joule of radiation energy, N is equal to E divided by H nu. How to bypass this formula? Number of photons present in 6.62 joule is what? What's the formula? N is equal to E by H nu. Then you have to substitute the values. So what's the value? E equal to 6.62 divided by what? 62 into 10 raised to minus 22. which is equal to 10 raised to 22 electrons are present. Okay. The de Broglie wavelengths associated with a photon, proton and a neutron are found to be equal. Okay, so the question, the de Broglie wavelengths are same for proton and neutron. Which of the two has higher values for kinetic energy? Okay, so you know that lambda is equal to h divided by root of 2 mk. Okay, so lambda means wavelength, h means Planck's constant, m mass, then k means kinetic energy. Okay, so the question is what? The de Broglie wavelength of proton and neutron same. So lambda p is equal to what? Lambda n. So you have to write this equation as h by root of 2 mp kp is equal to what? H divided by root of 2 m and k. Here k is a constant. So both sides k are same. So cancelled each other. So 2 root 2 then next equal to root 2 is also same. So it's cancelled. So mp kp is equal to m and kn. Okay. Then also you know that the mass of proton is less than the mass of neutron. Okay. mp is less than mn. So what happened is kinetic energy is, that is kp is greater than k. That is kinetic energy of proton is greater than kinetic energy of neutron. Thus the proton has higher values of kinetic energy. Okay.